All right. So when you are going to start the accept reject method, so first of all you need to find out whether they are going to cover each other or not. So in that one, we are finding that both of them are covering each other properly, right? So then after that, what we are going to do, we are going to introduce a null vector here. Okay. And I should start from the 0 and repeat u naught is the uniform distribution. One observation we are going to start to generate, then y equals to 10 pi into u naught. In the u naught is basically your uniform distribution and minus 0.5, and then f naught is your square root of pi by 2 and exponential of y is minus y square by 2 divided by 1 plus y2 square. That is your targeted density that you want to generate the random numbers, and m is your constant here that we are going to consider. Okay, after that what we are doing, in the u1 we are going to generate the uniform distribution again. All right, and after that we are going to apply this one. If u1 is less than or equals to f naught divided by m, so at that time vi equals to y. Otherwise, again y equals I equals to I plus 1. Again iteration should go above and generate the random number, and then again check this condition. Okay, and it should go up to the length of 100, means 100 random numbers I need to generate. Till that this loop should continuously run. All right, why we are using here repeat and break? Why we are not using the for loop here? Okay, and why we are not using the while loop? Why we are using the repeat and break command here? Because if you just see here in the accept reject method, it is saying that first of all generate the y from the gy and generate u from the uniform distribution from 0 to 1, and then check this condition, u is less than equals to fx divided by the m into gx. If this condition is going to be satisfied, x should be equals to y. Okay, I will consider whatever the y I generated from the gy, that will be my x. Okay, otherwise code should stop and it should go again in the beginning, and it should generate the y from gy and u from the uniform, and then again it should check the condition. So in the while loop and the for loop, what you have? In the for loop, you have the number of iteration. Okay, either the condition will satisfy or not, right? And in the while loop, what is the condition you have? Till the condition is going to be satisfied, it should run. All right, till the condition is not going to be satisfied, it should run. When the condition is going to be fulfilled, it should stop, right? So, but here, what we have? If the condition is satisfied, it should continue. If condition is not going to satisfy, it should stop and again go back. So in that one, what we are doing? We use the repeat and break loop. So repeat, all right, then the loop will start from here and you have the condition. If this condition is going to be fulfilled, okay, if this condition is going to be fulfilled, it should continue, otherwise it should break and go back again and generate the uniform distribution, u from the uniform distribution, and y and f, it should generate, otherwise again go for the loop. All right, so if we just check here, so we check this one and we got the v from the 100 v from the that one, our standard normal distribution for the Cauchy distribution, and this one, this curve is for your standard normal distribution, the blue one, and this histogram is for your generated values. All right, so if you will check, you will find that most of the values, means almost all the values are under this curve, in this blue curve. All the values are under this blue curve. Yes or no? This one, this is the blue curve, basically. Okay, this is your blue curve. So none of the values are going beyond this blue curve. Right. So means whatever the data you have generated from the standard normal distribution for your Cauchy distribution, that was generated perfectly. All right. And here it was covering properly. Your standard normal distribution was covering your Cauchy distribution properly in the first figure. In the second figure, it is showing the generated sample. So problem is that here, how to choose your M. Okay. The M that you are choosing here, where it is. This M. Okay. This M that we choose as the square root of 2 pi e raised to the power 1. That is the constant. But how you are going to choose that? That is the most difficult part. Okay. And what is M is basically defined as? M is basically defined as the, okay, see. Constant M is the maximum value of the function hx equals to fx divided by the gx with respect to x. What is the highest value of the difference you can take? Okay, M you need to select in such manner. So selecting M and selecting the distribution that should cover your target distribution, that is very important in the accept reject method. If you are not able to do it, so at that time you cannot go for the accept reject method. Okay, if you cannot find out the distribution that should cover your distribution completely, like that is accept reject method is not applicable for those methods, for those distribution which are very flexible, like generalized variable or generalized log logistic distribution, or some other distributions that are very flexible, what we should say here, which are more flexible. We have the modified variable also. We have TJ distribution is very flexible. Okay. Top Leon is very good in the flexibility. So when you have the distribution that is very flexible. Flexible means that if you are going to change the value of the parameter, suddenly the shape will change automatically. Okay. Because in the Cauchy and in the normal, what is the thing that whatever you will do, okay, whatever the parameters value you will change, okay, whatever the value of the parameter you will put, the shape will remain bell curved only, right? But if you just go to the that one generalized variable or variable distribution, if you just say you have the density for the variable distribution, right? So if you just see here in the variable distribution, this is the density function of the variable distribution. So if you just see, as you are changing the value of the parameter, you are getting the symmetric, you are getting the exponential shape also, you are getting the gamma distribution shape also, right? All three distribution shape you are getting here, right? So how you will approximate any distribution that should cover all this type of shape? It is very sensitive at that time. To find a distribution that will cover every single time the shape of variable distribution, it will be very difficult at that time. Yes or no? Right. So that's why accept reject method is not applicable or not suggested in such manner when you have the very flexible distribution, because it will becomes very difficult to find out the your proposal distribution that should cover your targeted distribution. Okay. like variable, like gamma, like exponential, like your Rayleigh, you can use it. Okay, because at that time they have the fixed shape that is not too much flexible. But in these distribution, it cannot be applicable, or it will becomes very difficult because every single time you need to change the value of the parameters of your proposal distribution also, and you need to check every single time whether it is going to cover your targeted distribution or not. So that is the limitation of your that one accept reject method. Okay. So yeah, this is the example of that one, your Cauchy distribution. So if you are, how you will find out this one in the Cauchy distribution, how you will find out the hx, that is your the different maximum difference, that is your fx divided by the gx 1 upon root 2 pi e raised to the power minus x by 2 divided by 1 upon pi into 1 plus x square. So square root of pi by 2 here you have, because pi will cancel out. So 1 plus x square into e raised to the power minus x by 2. So pi by 2 is a constant. So either you consider it or not, that is doesn't matter. But 1 plus x square into e raised to the power minus x square by 2, that should be your m when you are going to choose the Cauchy distribution. Okay, when you are going to choose the Cauchy distribution and the variable that one normal distribution, that should be your value of m, because it will change when your x is going to be changed. Okay, so that is the problem with uh, accept reject method limitation. So here you have the another code for the simple code for accept reject method, that you generate the x number from the R Cauchy distribution and 0 comma 1 standard Cauchy distribution. U is equals to R uniform distribution from 0 1. X is equals to x into u less than equals to d norm x that you are generating from the that one Cauchy distribution you will put here, and between 0 to 1 standard normal distribution, and m into what is your m, uh, m was your this one. Okay, m into d Cauchy x 0 comma 1. Okay, and then you find out the histogram and mean and standard deviation. Okay, that is the code for your standard Cauchy distribution and standard normal distribution. All right. Is time up or we have a time? We have a time? Yeah, 7:30. So now we will discuss the Metropolis algorithm. Okay. So here, why we need the Metropolis algorithm here? So the major problem with the applying the Monte Carlo integration in the obtaining the sample from the some complex probability distribution Px. The root of this problem is in MCMC method. Metropolis algorithm use a method that is similar to the accept reject algorithm. It is quite similar. But suppose our goal is to draw the sample from some distribution p theta, where p theta is equals to f theta divided by k, where k is the normalizing constant. Okay, we were not using any kind of normalizing constant earlier, either in the uh, accept reject or nor neither in accept reject nor in that one Monte Carlo integration nor in the importance sampling. All right. So one of these advantage using the Metropolis algorithm is that the normalizing constant k is not need to be known. Okay. In the accept reject, you need to be known. You need to be know the m. Right. But here you don't need to know that one. In practice, when we compute the posterior distribution in the Bayesian methods, it is very complicated to obtaining the normalizing constant integral fx theta, fx given theta into g theta. So in Metropolis algorithm, developed by the Metropolis and Ulam in 1949, later by the Metropolis and others, that is Hastings also, was there, it generated a sequence of the draws from the distribution p theta by using the following algorithm. So what you need to do here, you need to start with the initial gas value theta naught. If you want to generate the value from f theta, so you need to start from some initial value f theta naught that should satisfy this condition. F theta naught should be greater than 0. All right, means because the density should be non-negative, right? Density function should be non-negative, so it should be greater than 0. If it is not greater than 0, you cannot use theta naught here. All right. So when you are going to choose the theta naught, you are independent to choose the theta naught, but it should satisfy this condition mainly. After that, using the current value of theta sample each candidate of the theta star from some jumping distribution. Okay, just remember the jumping distribution q theta 1, theta 2, which is the probability of returning the value of theta 2 given a previous value of theta 1. All right. So basically what we need to do, you need to use the, when you are going to generate the value of theta 1 and theta 2 and so on, so you need to find out, use some jumping distribution that you are saying q theta 1 theta 2, that is the basically probability of returning the value theta 2 given a previous value of theta 1. All right, this distribution is also referred to as the proposal distribution. The only restriction on this density in the Metropolis algorithm is that it is symmetric. Okay, q theta 1 theta 2 should be equals to the q theta 2 theta 1. So whatever the distribution you are going to assume here for your proposal density, that should be your symmetric. Okay, so mostly we use here the normal distribution as your, because normal is a symmetric distribution, right? You can use Cauchy also, but normal is quite familiar, quite easy to use because it is also symmetric and we can find out the probability of Q1, Q2. All right. So given a candidate theta star, that is your generated value that you are going to generate, calculate the ratio of the density at the candidate theta star and the current theta point, say theta t minus 1. So what you need to do basically, you need to find out the ratio that is your alpha. Okay. And you need to put the value here, whatever the value theta, suppose you are going to start, you want to generate theta 2. You want to use theta 2 and theta 1 is your current value. So that is your theta star and that is your theta t minus 1 from this one. So you will compute this ratio. So p theta star divided by the p theta t minus 1. That will be equals to f theta star divided by the k and f theta t minus 1 divided by k. So k will cancel out here. So you don't need the k also here. All right. So what they were using here in the Metropolis algorithm, they were saying if you can write your p theta equals to f theta divided by k in such form, where k was your normalizing that one. So you either don't know it or don't know it. That is not going to make any impact because in the last, when you are going to put these values, whatever the values you are going to generate, okay, of theta, that will be, you are going to put in the density function and that is density is basically divided by k only. So k will cancel out. So that is basically f theta star divided by the theta t minus 1. So after that, what you will do, how you will accept your theta here, how you will accept your theta. To accept your theta, you need to compare your theta star with this one. This condition, u should be minimum of 1 or alpha. So what you will do, you will generate the value u from the uniform distribution 0, 1, and after that you need to find out the minimum between 1 and alpha. Alpha is your ratio. Okay, alpha is the ratio of your current value. Okay. Sorry, the future value that you want to generate and divided by the current value that you are going to put in your density. So you will accept the proposed value if the uniform value is less than the minimum value. Okay, of 1 and alpha, else you will reject and again you will go back to the step 2 here and you will again generate the values. Okay, and so basically how you will summarize this one, alpha is basically minimum of your f theta star divided by f theta t minus 1 comma 1. Okay, and then you will accept the candidate point with the probability alpha and generate the Markov chain of your thetas here. Okay, how you will do it? Uh, Give me a second. Let me. So this is the code for the Metropolis algorithm. We are going to generate the numbers. Okay, we are going to generate the numbers from the gamma distribution. So what we are doing here, we have the density function of gamma distribution, right? That is a raised to the power b divided by gamma b x raised to the power b minus 1 into e raised to the power minus ax. So here we are going to introduce a null vector with 5000 observation and we are going to introduce another null vector with one of 2500 values. One is basically, after that we are giving the values of a and b here. Okay, for the given value of alpha and beta we want to generate the random numbers, right? So after that what we are going to do, we are going to run this code for loop up to 5000 times and we are going to generate the uniform 1030. Why it is 1 to 30? Is your candidate? Let me check this one. Why it is 5 only? Uh, Give me a second. This code is also not correct. All right. So here we have the distribution here that is generalized Lindley. In that one, we have the three parameters a equals to, and we are taking the values of a equals to 3, b equals to 8, and theta equals to 2 here. And we are going to generate the 5000 observations from the distribution. Mu is the basically the formula of mean of this distribution. All right. And this is your formula of variance, EJZ minus mu whole square. That is your formula of variance. So in that one, we are going to store the standard deviation is square root of variance. In Z new is we are going to introduce as a vector of numeric values of size n. That is the another method to store the values. All right. So here in this function, what we are going to do, we are introducing our PDF. Okay. And we are making it a function of Z because here if you just see, we have theta, A and B. All these terms are known, only Z is unknown because we want to generate the values of Z, right? So after that, we are going to start from the value of Z node, that is my 2.2. So what was the first condition for that one, for the Metropolis algorithm? When you are going to generate the value for the Metropolis algorithm, that should be f shed, f theta should be greater than 0. So for the positive value of theta, positive value of that one, Z, and theta and theta alpha beta all are positive. So PDF will be positive only. All right. So what I am going to do, I am going to say the first value of Z new should be Z naught. All right. Then I am going to start my for loop from 1 to 2 to n, because first value I am already assigning, that is my Z naught. All right. So I want to generate the 5000 values. So that's why it should start from 2 to n. All right. After that, I'm going to introduce my candidate or my proposal density is the R norm. All right. Here, what we were doing, we were introducing a density. Okay, jumping distribution. That is our Q1, that I am going to define as the, because it should be symmetric. So I am introducing it as a normal distribution here. All right. So what I am going to say, that if candidate is greater than 0, so it should consider, because normal, in the normal distribution it can generate the negative values also. Yes or no? What is the what is the limit of the normal distribution? Minus infinity to infinity. So if I'm going to generate the random number from the normal distribution with mean, mu and standard deviation, HD, that formula that I wrote here, so it can generate the negative value or not? This one. It can generate the negative value, right? But for the Lindley distribution is a lifetime distribution, means x is defined over the range of 0 to infinity. So minus or negative value I cannot consider here, right? So for that one I am applying a one condition: if the generated value can is greater than 0, so it should consider, otherwise it should take can equals to 0. If it is negative, so take it as the 0. So after that, what I'm going to do, I'm going to find out the probability, that is minimum. Okay, that is minimum F12. That is basically what I'm going to do here. That is for the Metropolis hasting, not the Metropolis only. Yes. This is for the Metropolis hasting algorithm, not for the Metropolis. I am going to remove this one. I need to remove this portion. So all the brackets are closed. 1, 2, 3 brackets are closed. One is open. So 2 is still open. 1 and 2. Okay, fine. So this should be the condition. All right. That is the condition of Metropolis. Correct. That minimum of f theta star divided by the f theta minus 1. That means what I am going to do here. So first value that I'm going to generate from the normal distribution can, and what is the my initial value divided by that, right? After that I will generate the one value from the uniform distribution, and I will compare both of them. U should be less than equals to less than probability. If this happens, so Z naught should be replaced by the value that I generated from the normal distribution. Otherwise, Z new should be equals to Z not only. Whatever the value, initial value I took, that should be remain as it is. Otherwise, it should replace. All right. So I am going to use that one. I will check. All right. So these are the values that I generated from the Metropolis algorithm. 5000 values. Okay. 5000 values that I generated from the Metropolis algorithm. Now I will check how better it was generated. So for that one, I'm going to check the trace plot. Trace plot is fine. And this is the density plot of my generated value. So it should generalized linear distribution is the positively skewed distribution. So if we just find out, this is the positively skewed distribution, right? And after that, we are finding the mean, that is 2.33. All right. And variance is 2.55, that I just from the formula that I gave in the earlier in the beginning of the code. Okay, from this code, okay, from this formulas, the variance and mean is 2.33 and variance is 2.55. And from generated values, the mean is 2.06, that is close to 2.33, but the variance is not that much big that I was getting from the formula, right? It is happening because I am generating the random number. Okay, so variance can vary this much. All right. So what you need to did you get this one? This code? Okay, so I will repeat it in the next lecture. Okay. I will repeat this code in the next lecture. Okay. I think time's up. Yeah, time's up. So we will talk about all these things in the next lecture. I will repeat it. Okay.